We saw in our last video that gas under the influence of gravity has slightly more pressure at the bottom of its container than at its top. Now, if the container is a small container, like something you might use on a human type scale, then we can essentially assume that this difference is very, very small, and we can assume that the pressure is the same everywhere. But if we start to look on large enough scales, really big containers, like containers the height of our entire atmosphere, then it becomes much more clear the effect that gravity has on the gas inside the walls of our imaginarily hugely tall container. So, because the density of the gas molecules is much higher, close to the Earth's surface, that's where the pressure is going to be the greatest. And as you move up towards the outer portions of our atmosphere, closer to space, the density and the pressure gets smaller and smaller until it essentially approaches zero. And again, we saw that there's no perfect vacuum, but space is pretty close. So this is very similar to what we see with liquids. We just need larger containers to be able to notice this difference. Since atmospheric pressure, the pressure due to our own atmosphere, decreases with height above Earth's surface, we define a standard atmosphere as 100 and 1,300 pascals, or 101.3 kilopascals. Now, this is technically only true at sea level, but unless otherwise stated, you can assume standard atmospheric pressure in any problem that you run into. The SI unit for pressure, again, is pascals. So if you see the pressure written in terms of atmospheres or kilopascals, you will need to convert it in order to be able to do your calculations correctly. Now, how exactly does atmospheric pressure work? So if we imagine some small object, that object is under atmospheric pressure, which means it's experiencing forces from all around itself. Fluids exert forces in all directions. So if we think about your arm, we can lift our arms because the atmospheric pressure is not only pushing down on our arm, it's also pushing up on our arm and in and out in all directions. So the net force on our arm due to atmospheric pressure is essentially zero. So that means you don't have to work against these forces to be able to move your arm. The net force is zero, so you just need to be able to apply whatever force needed to make it move. Now, what about vacuum cleaners and suction cups? So this is what happens if there's no air on one side. So if we were to go through and take away one of these forces, now we no longer have a net force of zero. We'll have a net force in this direction. So this is essentially what a vacuum cleaner or a suction cup does. The vacuum cleaner is removing air from one side. So if you put your hand against the end of a vacuum hose, you're going to feel it being pulled towards that vacuum. It's actually not being pulled, it's being pushed. So there's no force between your hand and the vacuum cleaner because the air has been removed or is continually being removed. But there is atmospheric pressure on the opposite side of your hand, pushing your hand up against that vacuum cleaner. Similarly with a suction cup, when you push your suction cup up against the wall, you remove the air between the suction cup and the wall. Because that air is not there, the atmospheric pressure on the opposite side pushes that suction cup up against the wall, keeping it in place. Let's go through and take a look at an example that goes through this. So in our example, we have a 10 centimeter diameter suction cup that's pushed against a smooth ceiling. What is the maximum mass of an object that can be suspended from this suction cup without pulling it off the ceiling? So to start, let's take a look at the free body diagram that we already have included here. We have the force due to the air around it pushing upwards, again, pushing in the direction of which there is no air. So we can see that pointing up. We have the gravitational force of the suction cup and its mass pulling down. And then we have the normal force of the ceiling. If there's any sort of contact, then you have a normal force. So that means our net force is going to be that normal force plus the force of gravity minus the force due to the air around it. And if it's not moving, this net force is 0. So we can rearrange this to solve for the force of the air. That's going to be the normal force plus the gravitational force. That force of the air is equal to the pressure times the surface area. The surface area is going to be pi r squared, where r is 5 centimeters. And the pressure is the air pressure around us. So again, it's not specified, so we're going to assume the 1 atmosphere. So that's 101,300 pascals times pi times 0.05 meters squared, which gives us a force due to the air of 796 newtons. Now what we want to find is the maximum mass of an object that can be suspended from this suction cup. So in order to find the maximum mass, we imagine that the gravitational force is becoming larger and larger as we increase the mass of this object, because the gravitational force is just mass times g. Now imagine that we're able to increase it enough that that normal force goes to 0. We can figure out what this maximum gravitational force is then by assuming that normal force goes to 0. Anything larger than that, your gravitational force is going to be larger than the force due to the air. So our largest the gravitational force can possibly be is the same as the force due to the air, the 796 newtons. That's equal to mg. So if we solve this for mass, we find that the largest the mass can be is 81 kilograms.